Have you ever wondered why your voice sounds different to you than it does when you hear it on a recording? And just a quick question, how many of us like what we sound like on a recording? Let's see, raise your hand. Lying. Yeah, not many of us. Most of us like what we sound in our head versus what we sound on a recording. If you record your voice on your cell phone or something like that, we don't like what that sounds like. Well, I want you to try something. I want you to say out loud the word girl. 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 I know what that sounds like. Now I want you to take your hand. I can't use this hand. Take your hand. Kind of do it like a little hole, like so. Put it up to your mouth like that, and then say it again. Girl, 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 girl. It sounds way different. Why does it sound different? What is my hand doing? Today we're going to explore that. We're going to explore wave properties such as interference. We're going to explore wave properties of destructive and constructive interference. We're going to talk about resonance, and we're going to talk about natural frequencies. All of that is going to get to why my voice sounds different when I do different things, and specifically why my voice sounds different in my head than it does when it's on my cell phone. The next question I have for you is, which one of those voices is correct? Is it correct what I think I sound like? Or is it correct when I hear my voice on a recording? Recording obviously maybe has some like disruptive properties to it because of all the electronics that happen in a cell phone. Who knows? So we're going to discuss all of those features. Before we do that, we're going to take one small step back just so I know that you and I are all on the same page when we're talking about weight. Okay, so you've seen this animation before, but I've never really explained it. It was up to you to kind of look at it and understand what's going on. So up here we have a longitudinal wave. There are two examples of longitudinal waves that we want to talk about. The one that we will talk about most are sound waves. And I've been talking about sound waves the most because that is, most prevalent to our life here in the Northeast of New England. The other type of longitudinal waves that may or may not affect us are earthquake waves. There are two types of earthquake waves, and this talks about it. Primary waves, P waves, and secondary waves, S waves. Primary waves are waves that go back and forth, and those are the waves that are called the primary wave for an earthquake. Why is it called the primary wave? Maybe it's the first wave. I don't know. Look, there's a link right there that you can look at and read about. That's not our focus today. Our focus is what's going on in this little animation. Here you have it's like a bar, and that bar is oscillating at a constant frequency. Oscillating just means back and forth at the same frequency. And you can see in both pictures that there's this dark spot that seems to move all the way down the screen, and then there are these open spots that seem to move all the way down the screen. Those have specific names. The dark lines are called compression, and those compressions propagate or move all the way down the screen. The open spots are called rarefaction spots. R-A-R-E-F-A-C-T-I-O-N. Rarefaction, one word. And those also seem to move all the way down the screen. Now, just like a sound wave, those particles, if you notice, they highlight a red particle there. They put an arrow on these two. You can pick any particle in this whole thing. I can put the cursor right there under that group. And you will see that group, they just oscillate back and forth. They don't actually move because waves move energy. They do not move matter. So for a sound wave, the waves that I like to talk about, the air right in front of my mouth hits an air molecule, hits an air molecule, hits an air molecule, hits an air molecule until it gets to you. So the speakers where my sound is coming from, my voice is coming from on your computer, unless you're wearing earbuds, which would be just closer, the sound hits an air molecule to another one, to another one, to another one, to another one, until it gets to you. Otherwise, when we're in class, I drink coffee all the time. I'm a coffee fiend. You would smell my terrible coffee breath all the time if I'm in the front of the room, if the air right in front of my mouth made it all the way to you in your seat. That's not what happens. It's just a collision, it's excessive collision of air molecules until they get to you. That's also why when you yell, your voice loses energy as it goes down, right? I can yell, it's really loud up by me when I go, really loud up by me, but further away, it might not be as loud because as those air molecules collide, as any two objects collide, that collision takes energy. So there's a loss of energy with every air molecule collision. Now, sound travels in all three different mediums, in solids and liquids and gases, and sound travels the slowest in a gas because the molecules are so far away. That molecule over here hits a molecule over there, hits a molecule over there, and because they're so far away, that takes more time. So sound travels the slowest in air. Then in a liquid like water, sound travels a little bit faster. So like if you've ever been underwater and there's like somebody's watch beeping, like an alarm or something like that, it sounds like it's kind of loud, louder than in air. Well, that's just because their molecules are so close together, it's traveling faster, so it gets to you faster, losing less energy, so it sounds louder. In a solid, where the molecules are packed really, really, really dense, sound travels the fastest because it is just bump, 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 bump right next to each other. So when I hit the table as hard as I can, that energy propagates through, but like I said, it goes really fast. But the table molecules, the wood molecules, didn't go anywhere. They just vibrated just like this animation, back and forth. Now, every other kind of wave you can think of that's not a sound wave or a primary earthquake wave is a transverse wave. Now, these are the waves we picture most of the time because they're easier for us, but the same thing happens. If you notice, look at any group of molecules. Those molecules just oscillate up and down. Those molecules oscillate perpendicular to wave motion, as these molecules oscillate parallel to wave motion. Now, same idea applies. These waves transfer energy. They do not transfer matter. And then the last wave, and we don't really talk about these waves, but the same rules apply, are these surface waves. And you can see these surface waves seem to travel in a circle. These are like water waves. And that happens no matter where you are in the water. Obviously, the further down, the less interference there is. But they travel and they have this circular motion. But if you notice, the displacement of the wave particles are still zero. Again, because waves transfer only energy. Now you might be thinking to yourself, but I've seen people surf and water often brings in like trash and things onto shore. Well, surfers manipulate the surface of the wave such that they're riding that energy in. That's what they're doing. If they weren't coming on that angle, if they were just trying to go perpendicular to the wave, they wouldn't go anywhere. So if you notice when a surfer is surfing, they're going on an angle with the wave. So they are manipulating the wave so they can surf. The trash and things, any current or undertow, that also has an effect, and that is something totally different from the wave. That's a property of the ocean itself. So those are different things and different ideas that you may think, that you may hear, but what we need to know and understand is a wave transfers only energy. A wave cannot transfer matter. Now that we really have an idea and understand that, again, we're going to talk about wave interference. We're going to talk about constructive and destructive interference. We're going to talk about natural frequency and resonance. So the first thing we're going to talk about is wave interference and the principle of superposition. Now remember, waves are just energy. They're not physical things, which means I can get one wave traveling and another wave traveling to interfere with each other. Anyone that sings or plays an instrument in a band or a chorus, you know this is harmony. You want all of our waves to go and interfere with each other so the group sounds really good. Everything is louder, everything is in the same tone or the same frequency, and it sounds good. Now you're thinking, why the heck are you showing me, Mr. Rose, a picture of you playing baseball for the New York Mets and catching? Look, there's me catching for the New York Mets. Woo! Haha, no, that's not me. That is just my face superimposed on a Mets player's body with those awesome glasses. So we already knew what superposition was. A lot of us have played with superposition before when we put one object on top of the other. So here we physically cut out my head, put it on top of this picture, and now I have a superimposed image. So that is the law of superposition, and waves obey that law. So when I have two or more waves and they interact in such a way, I can make the crests, the top part of the wave, I can make the crests bigger to have bigger amplitudes. I can make the troughs bigger to have bigger amplitudes. And when those two things happen, we cause interference patterns. We cause constructive interference patterns, where the waves get bigger on the top and on the bottom. And we have destructive interference patterns, where the waves totally cancel out. And all of a sudden it would go from like a loud sound, and then it's going to bigger and bigger and bigger and bigger and bigger to a big sound, and then it's getting smaller and smaller. So those are two examples, and I'm going to show you what that looks like. Okay, so check this out. We have one wave and we have a second wave, and these are both transverse waves. Now remember, both transverse waves and longitudinal waves act in this fashion, but it's easier to demonstrate with transverse waves. So when these waves travel towards each other, and I can control that, you see I have one wave on top of another wave, and now when I have, there we go, this crest on top of this trough, what do we think happens? Well, this crest, the medium this is traveling through, can fall into this hole, into that trough. So the sum, when I put the sum together, that looks like, get rid of wave 1 and wave 2, it is canceling each other out, almost that flat line. And it's almost a flat line just because I didn't line them up perfectly. So when you see the waves on top of each other, and this is called 180 degrees out of phase, this is a total, there we go, a total cancellation of sound. And there are demonstrations I'm trying to figure out how you can set them up at home where you can see this, where you can physically hear dead spots in sound, because one wave is physically on top of the other wave and it cancels it out. This is called destructive interference. Now, as the waves continue to propagate, going to get rid of that sum again, the waves keep moving just like nothing happened, because waves are just energy. So they superimpose on top of each other. And there we go. Now we have one wave directly on top of another wave. So they're superimposed on top of each other. That means instead of an amplitude that is that high, the amplitude will be twice as high because the waves are now building up. This is called constructive interference, where the waves construct and build. So this would be, if you were hearing it, something that is louder, a louder sound. The amplitude gets bigger in both the crest and the trough. Remember, amplitude is measured from the medium to the very bottom of the of the crest. Oh, that's a trough. The very bottom of the trough, or the very top of the crest. Now I'm going to rewind these guys, and I'm going to go to automatic. There we go. So now we can see it happen live as they go back and forth. All right, they're going to bounce and now come back. A crest on top of a trough. The white line is the sum. You see it cancels out and then gets bigger and smaller. And then the waves continue to propagate just like nothing happened. This is just super slow motion of waves. So you saw where it flattens out. As the two crests get on top of each other, the two troughs get on top of each other, gets bigger and bigger and bigger to show that constructive interference. Then you'll see the crest on top of the trough, destructive interference. And then it keeps going like nothing happened. They don't even care that they were interacting. Now that you know a little bit about wave interference, constructive and destructive interference, we're going to talk about standing waves. So here you see the inside of a piano. You can also think of a guitar string. And what happens when I pluck a guitar string, because all the strings look like they're about the same length, or in the piano, if you open up a piano, all those strings kind of maybe look like they're the same length, they sound different. So that's a standing wave. And That's because the thickness of each string is different, and where the string is pinched off is a little bit different. So when you pluck a guitar string, it goes bang, vibrates back and forth. Plug a different guitar string, it goes bang, and vibrates back and forth. Well, the two ends of the guitar string that are pinned down cause the waves to reflect, because waves are allowed to do that. An echo, for example, is just a wave bouncing off something and reflecting back. That's an echo, like echolocation in the video you've seen before. So all that's happening with the wave is a standing wave is when a wave reflects and then interferes again with itself. Or when two waves that are the right frequency interact in such a way that it looks like the waves are standing, or instead of like that propagating motion from left to right, the waves kind of just oscillate up and down. It kind of looks like they're not moving. So we're going to take a look at that. So here's a standing wave with two fixed ends, one there, one there. Now, the first thing I want to say is there is a one half of wavelength here. If I pause, I go from here to there. There's one crest, but there's no trough. So this is only a half wavelength. And this is called the first harmonic, or a fundamental frequency. That's a pure tone, right? And the pure tone means we have a perfect standing wave from one side to the other. So the wave propagates from one side all the way to the other side, and then bounces back, and it looks the same. So when I play this again, we see that oscillation going up and down. Now, a standing wave has specific parts. Here, this tells me that the biggest portion of that is called an antinode. The antinodes in a standing wave are where there is a maximum interference. So that means the biggest trough or the biggest crest. Then the nodes mean no movement. So on a guitar, that's where the end strings are pinched, and those are your reflection points. Literally, if this was a string, you could put your fingers on that node and it wouldn't vibrate at all. It wouldn't mess up my wave. But if I put my fingers right on the antinode, that would be a problem. So an antinode means not moving, or moving, because we're physicists, we make things complicated. Nodes mean no movement. Now, here we just see, it kind of looks, as they say, like this envelope kind of thing. That's okay. Where it is just the top portion and the bottom portion. This shows the maximum interference on the top and the bottom. And it shows that the wave doesn't look like it's propagating, it's just moving up and down. And this happens when you are at an object's natural frequency. In other words, it is the easiest way that string can vibrate back and forth, making that pure tone. It does happen with more than one wave. Here we have two waves now. And I shouldn't say two waves. Here we have two sets of interference. So the wave is reflecting such that, I'm going to pause it. We see now that we have one full wavelength, but those waves just go up and down. This is called the second harmonic for, again, this specific medium. Guitar strings do this, piano strings do this, and they vibrate differently. I'm going to show you an example of that as well. As we go forward, nothing has changed with our vocabulary. We have three nodes. You can see no movement, no movement, no movement, and two antinodes. Here, maximum interference, maximum interference. Now let's use some of those words. Those nodes are places where there is destructive interference taking place. You're going to see that in a minute. The antinodes are where there is constructive interference taking place. Here you can just see that it is actually one wave that is oscillating back and forth, making that pure tone or pure harmonic at its natural frequency, the easiest frequency such that it vibrates back and forth. This is just like a future video where you're going to see a bridge actually go under this wave interference called galloping Gertie. Same thing, now I have 1.5 waves, and we can really see where that constructive and destructive interference is. And as you can see, as I'm clicking through these, the more waves we have, the faster they oscillate. Because remember, we're assuming this is the same medium, like the same guitar string. So I go all the way back. Look how slow this one oscillates. This is our first harmonic and only one constructive or destructive interference spot. I'm sorry, one constructive, two destructive interference spots. But this is a half of a wave. Now as I go to one full wave, the oscillations get a little bit faster. The frequency increases. This was sound higher. As I go to a wave and a half, it gets even faster. The frequency is changing. The velocity of the wave in that material would be exactly the same. There's one more, even faster. Now I have two complete waves you can see. One wave, two complete waves with 1, 2, 3, 4, 5 nodes and 1, 2, 3, 4 antinodes. No matter what it looks like, the wave frequency is increasing, the wave period would be decreasing, and the wave velocity would stay the same. Here you just see it's labeling all of our nodes and antinodes again for you. Okay, so here I only have a 4-second video, so I'm going to explain what's going on first. The bottom, let's start with the top actually. The top we see a wave in red and a wave in blue. And you can see right now they're in phase. In other words, the blue crest is right underneath the blue crest for a maximum constructive interference. The red trough is above the red trough for a maximum destructive interference. And you can see the purple line here, that's what's taking place there. Those waves are showing that there are two waves, and even though I have one on top of the other, we're going to superimpose them on top of each other, such that we show that interference pattern. Now in this 4-second video, what happens, you'll see the waves on top and the bottom move. I'll show it more than once. They move in opposite directions. As they move in opposite directions, they will have a maximum and a minimum interference point. I'm going to play it once through. And we'll show that again. Whoops. Sorry, one more time. All right, so you see here where I have the crest and the trough right on top of each other. That is a maximum, destructive interference pattern. So you can see, I don't want to move the cursor because that's going to bring up that play button again. You can see the purple line across the screen on the bottom. That is showing our destructive interference pattern, where it's easier to see the red crest on top of the blue trough. Obviously, those fall into each other. But the other is true too. When they're 180 degrees out of phase, the blue crest and the red trough, they meet, and those also cancel out. So the purple line is that total cancel out. And when they're building back up, then we see again those maximum constructive and destructive interference patterns. We can see the nodes and the antinodes. So like here's an antinode, here's an antinode, the node there and the node there. And as those waves travel, they travel and superimpose on top of each other for constructive and destructive interference. Okay, so now we're going to do an example that you can do at home, and you're going to be able to do it way better than me. I have here a wine glass. It's not the best wine glass, and I have in my right hand a broken wrist, so I can't do this very well. But try it at home, and hopefully you're going to get some understanding out of this. So I'm going to focus on my glass. So what I'm going to do is I'm going to put my hand on the bottom of the stem of the wine glass. The wine glass is full of water. Now, depending on the glass, it's easier to do. Some glasses have an easier shape. This is actually a very hard shape to do. And I want my face to be in it because, you know, you want to see my awesome looking face. Dip my hands in the water and nothing happens. If I go really fast, nothing happens. If I go slow, there's a little bit of sound, but it's not the best glass. What I'm trying to do is I'm trying to resonate the glass at its natural frequency. Now, that means it's kind of like pushing a swing. I'm going to try and get this glass to vibrate at its easiest frequency to vibrate. And that usually makes a nice sound. Now, my wine glass doesn't make a nice sound, but the whole thing crazily starts to shake if I get it real good, and you can see that. So I'm going to try and move the camera directly. All right, now hopefully we'll be able to see this. And we can see maybe the water. See those waves happening in the water? That's because man, that was actually a really good example. So what was happening there, and that really kind of hurt my wrist, so I'm going to stop. You could hear a little bit of the sound, and you could see the water jumping up on the glass. So what's happening is I am moving my hand at the right frequency, the right speed, or cycles per second around the rim of the glass. That's making this glass vibrate, which in turn is making the water vibrate. When you get it to move at that perfect frequency, if the glass is built right, a better looking wine glass than mine, ask your folks, don't break it, but you get to play a whole lot of nice sounds. The different water levels, as I have water high or water low, will control the natural frequency of the glass. A really nice glass you can get to vibrate with 0 water in. But as you change the level of the glass, the tone will change, and the frequency which you move your hand around will also change. So that is everything I have to talk to you about: natural frequency, resonance, and constructive and destructive interference. All of those things play in. Oh, I got this big like halo effect over my head. Woo! All of those things play in to how we hear different sounds. Now, I started with why do we sound different in our heads than when you record your voice on a cell phone? And I also said, say the word girl out loud. Girl, 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 girl. Then take your hand, make a little tunnel, put it up to your mouth, and say, girl, 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 girl. Sounds totally different. Well, when I put my hand in front of my face like that, and the word girl, for whatever reason, has the right tones in your voice, that the waves bounce off the inside of your hand, some of those sounds are absorbed by your hand, because we know energy can be absorbed. Some of those sounds reflect, and we're ending up with constructive and destructive interference in your hand, which is then changing the frequency of what we hear. When you speak out loud, like I'm doing here, I hear my voice not once, but twice. I hear my voice in the air because it is in the air bouncing off of all those air molecules, and my ears hear all that. I also hear my voice through the little bones in my head. Like if you hum, you can actually feel some vibrations in like the side of your head. So you hear your voice twice. That resonant frequency, because I'm making those little bones in my head resonate, and the sound of my voice in the air. The combination of those two sounds, the constructive and destructive interference, is what you hear. And for whatever reason, maybe it's because we hear it all the time, we mostly interpret that as a nicer sound. So I like the sound of my voice better than when I hear it on a recording. When I hear it on a recording, I feel like it's kind of annoying and obnoxious. Well, you are now hearing my voice on a recording, that annoying, obnoxious sound that I just talked about. When other people hear your voice on a recording, they hear that annoying, obnoxious sound that you don't like. That is the sound that the rest of the world hears. You actually never hear the sound of your own voice unless you're listening to a recording. If recording devices didn't take place, you would live your entire life without actually knowing what you sound like. Think about that. That's all I have for you today. I'm going to ask you to comment on this video. It's been a long video with a lot of information. So be sure to comment. And that's it. If you're watching this on YouTube, by all means, feel free to subscribe to my YouTube channel. Feel free to like, comment on there, or subscribe to the channel. Thanks for watching. See you all soon.